Okay. So welcome to this new session of PRIMO Talk. We're very glad to announce today's speaker, who is Martin Húska from University of Bologna. Martin got his master's degree at the Slovak University of Technology, which is based in Bratislava, and then he moved to Italy, where he joined the PhD program in Applied Mathematics at the University of Padova under the supervision of Professor Serena Morigi. He got his PhD degree in 2018, and since then he has a postdoc fellowship at University of Bologna. He mainly works on variational methods for image and geometry processing. And today he's going to give a talk about the composition of functions on surfaces. So please, Martin, the stage is yours.
All right, so thank you for the organization and also thank you for having me. Today I will talk about sparsity-aided variational model for additive decomposition of functions on surfaces. This talk will be based on two different papers in collaboration with Serena Morigi and Alessandro Lanza from University of Bologna, Ivan Selesnik from the New York University, and Sunga Kang from Georgia Institute of Technology. So first, I will give an introduction and a couple of related works regarding the decomposition. Then I will present our piecewise smooth decomposition model. I will give some details on its discretization and solution strategy, the so-called convex non-convex strategy. Just a quick idea about the numerical solution, some experiments, and then I will present a step further of this model, which is sort of an enriched model regarding the one I will be presenting. So for the additive decomposition, the the goal or the idea is to separate the observed signal image or a function into some meaningful components, which in addition represents the input signal. The choice of these components depends, however, on the application we want to use it for, since we can look for cartooning or posterization of an image, or separation of a texture, or just a simple denoising, then soft shadow or soft spotlight removal, or to retrieve the structure underlying in the observed signal. The early works, starting with Mayer and followed by Aujour-Chambol and others, focused mainly on the so-called structure, texture, and or noise decomposition, where structure is represented by a piecewise constant component, texture is an oscillating zero mean component, and noise was assumed to be Gaussian as well with zero mean. Later on, Golami and Hosseini, and followed by Selesnik, proposed a piecewise smooth decomposition model for 1D signal denoising that could be extensible also to images, where once again the structure was the piecewise constant trend in the observed signal, and the smooth component was a slowly varying component or harmonic component in the signal. So in Aujour-Chambol have proposed the following model, where they tried to decompose an observed image F into structure V, texture W, and noise N, where the Regularizations in this model were consisted of total variation and then a dual norm or to the total variation, or a G norm, we could say, and another norm, which is a dual Bessov norm represented by Banach space. The definition by Meyer and his G norm, a G norm of a component or of a function W can be expressed in the following way, assuming that there is a vector G or a vector field G whose or which divergence is equal to the component we are looking for, where the components of this vector field are from a given space Y. For the G norm, Y is the Meyer's space, and for the other component, it's the following Banach space. As an example of the results of this model, having an original image composed by the horizontal stripes and a square in the center, the authors corrupted it by the following noise with standard deviation 35 in terms of images in between 0 and 255. And here are the three resulting components. So for them, the structure is the square in the center. The texture is represented by the horizontal stripes, and this is the noise component. The other work by Golami and Hossein in 2013, they proposed the following combination of total variation and Tikhonov type of regularization for denoising of a piecewise smooth signal, where once again the fidelity term is the same. In this case, it does not just tie the two components together, but it also is used as a L2 norm for to handle the noise. And H is a second order derivative operator. So therefore, their results can be represented from the original and the noisy corrupted image as the denoised result. I just mentioned quickly that since I will be talking also about functions that are defined over connected to manifold embedded in R3, so it is mapped from the surface to RD. In my case, D is equal to 1, since I will assume just the scalar functions, not vector fields over the surfaces. And a way, of course, the scalar functions defined over surfaces can represent different properties of the surface itself. For example, a temperature or the mean curvature field or the scalar mean curvature field, a texture or a grayscale image or a different scalar property, such as shape diameter function. And the way how to visualize them is to assign a false color to the points according to their attained values, such as you can see here And this is also the scale I will be using. So moving to our proposed model, we have focused all on the piecewise smooth decomposition. In this case, where we have assumed that our piecewise smooth image is represented as a combination of a piecewise constant and smooth component, which is corrupted by noise. Therefore, we also have incorporated a fidelity term and two regularizations with a single trade-off parameter eta and lambda as a trade-off parameter to handle the noise. For the smooth component, the penalty is a classic quadratic penalty, while for the piecewise constant or the structure component, we have used a non-smooth, non-convex penalty function phi that depends on an additional parameter a, which can be called also a degree of concavity of this function. Therefore, our model is non-smooth and non-convex. The penalty function phi we have used is a rescaled and reparametrized version of a so-called min-max penalty, which falls into the family of separable parametrized non-convex penalty functions. It can be defined in the following way, and on the right you can see some graphs of these penalty functions for different values of the parameter a. As you can notice, increasing a, the transition points from the concave part to the plateau is moving towards zero, and therefore for a that goes towards infinity, we can recover an L0 norm. Vice versa, for a going towards zero, the behavior becomes more like a total variation, convex total variation. One of the important properties of this family of penalty functions is that their second order derivative can be bounded from below by the value a itself, which poses an advantage with respect to LP norm, which can for p below zero, below 1. So in order to discretize our model, we should stop quickly at the discretization of the domain, for which an embedded manifold is usually represented by an approximating mesh, which consists of the set of vertices V, triangles T, edges E. And the structure allows us to define also two additional sets, which is the first ring, that is a set of the first neighborhood vertices to xi, and the first disk, which is the set of the incident triangles at xi. Once we have our approximating mesh, the next thing is to consider the sampling of the observed function. In general, we have two options. One is to assign the function values to the triangles, which lead to a piecewise constant representation of the function, or what we have used is a piecewise linear approximation for f being sampled on the vertices themselves. Due to the piecewise linear approximation, the gradient operator can be discretized as a combination of gradients of the basis functions b, which are expressed in the following way, which is nothing else than just a vector pointing from the edge towards the center vertex xi. Moving to the model discretization, we have used a simple quadrature formulas in order to arrive to the discretization. And we have used the fact that the gradient is constant over the triangles. Therefore, in the discrete form, we can write our functional as a sum over the mesh triangles. In the vectorized form, the areas of the triangles and around vertices, which arise from the quadrature rules, can be incorporated in matrices SV and S, which are diagonal matrices. As well, the global discrete gradient operator can be represented by a matrix D that has 3 times dimensions, 3 times number of the triangles times the number of vertices. This matrix is highly sparse, and in total it has just 3 times the number of triangles of non-zero elements, which consists of the gradients of the basis functions. In the special case of images, of course, the gradient matrix D can be represented just by the usual forward finite differences, while the area matrices S and SV cancel out. So now that we have our model, which is discretized, the question is how to solve the optimization problem, because of course the convex optimization has a lot of advantages with respect to the unicity and global solution. However, the non-convex sparse optimization usually does better in terms of the quality of the reconstruction. Usually, like iteratively weighted norms is used in case of non-convex optimization, which is still a convexification of the model. In our case, we have used the so-called convex non-convex strategy, where the main idea is to balance the negative second order derivative of the non-convex penalty, in our case phi, with the positive second order derivatives of the quadratic terms. So in our case, the fidelity and the regularization on the smooth component. For this strategy, the pivotal works were done by Blake and Zisserman, followed by Nikolova and Selesnik. So just a simple example of the convexity conditions for this ROF type of non-convex ROF. The condition on the parameter A in phi can be expressed simply as follows. Therefore, if we introduce a convexity coefficient tau c that multiplies a bar the threshold value, this allows us to even play with different regimes of the model itself. Of course, if we take tau c equal to 0.99, we are sure that we are in the overall convex regime. However, maximizing the non-convexity of the penalty term. If we go with tau c over 1, we switch to purely non-convex regime, and for tau c that goes towards 0, we arrive to a TV regularizer. For our model, the threshold A bar is slightly more difficult. Nevertheless, it still depends just on the model parameters and a value Emax, which is the maximum of eigenvalue of following matrix B. Just a quick sketch how we arrived to this condition. First, we have rewritten our functional J into sum of J1 and J2 plus a affine function depending on VW. And then we studied the convexity conditions for J1 and J2 separately, and then we put them together, maximizing the value of gamma. So for the ADMM, which is the alternating direction method of multipliers that we have used, we have introduced an auxiliary variable t that's equal to the gradient of v, and a variable x, which consists of the piecewise smooth component or the piecewise smooth resulting image u and the structure component v. So using this change of variables, we still lead towards a two-block ADMM minimization, for which the Lagrangian function is the following one, where beta is a scalar penalty and the rho represents the vector of Lagrange multipliers. Therefore, iteratively, we need to solve just the subproblem for x, t, and the closed form update for the Lagrange multipliers. For x, thanks to the change of variables from VW to u and v, we can even decouple the two linear systems. And for the t subproblems, we arrive to, since the penalty function is separable, we arrive to smaller subproblems of this form for each triangle in the mesh. Since the phi penalty is present in this subproblem, and we have done all the work to have the overall functional convex, we can study the convexity of the subproblem as well, which is summarized in proposition 2. And applying proposition 2, we can add an additional constraint on the value of beta, such that all the subproblems for T will be convex as well. In that case, the shrinkage operator that represents the solution for this subproblem has a closed form as for in the following way. So quickly, I should talk about separability. In fact, when we can say that two components are separable, this is an additional assumption we need to make, because otherwise one part of one component which we may assume to be smooth can end up in the piecewise constant component and vice versa. So these two components, W and V, are separable if the histogram of their gradient magnitudes can be separable. In particular, the minimum non-zero gradient magnitude and the maximum gradient magnitude assigned as small and capital M needs to be apart, creating a separation region in between them. What I mean by that is that if we, as we did a test case for changing values of eta, as you can see down here, what happens to the model is that as we change the value of eta, we move the abscissa of the intersection point between the quadratic penalty and the phi function. And above here, you can see the two components V and W, and how an image can be separated in this case. So when the intersection point is away from the region, from this region, also indicated here by the vertical bars, the components can be shifted, and also as the intersection point moves closer to the separation region, we can start seeing some parts of the piecewise constant image appearing. When we are inside the separation region, the separation is perfect, and if we move once again beyond the separation region, the two situation flips more or less. This led us to define a way how to set the parameter eta, but I think I can skip that. So moving to some experiments that we have done, what we have studied is the image decomposition in case of the following image containing the two components, which was then corrupted by noise, and we have applied three different values of tau c in order to see how the different regimes of our model can perform. So for the total variation, or tau c, going toward 0, the separation is not so good. I suppose this is mostly due to the fact that TV usually underestimate the image intensity. Our proposed convex non-convex approach with respect to non-convex regime of our model provides comparable results. Of course, in our case, we can say that we have arrived to a global minimizer, where for the non-convex model, we have used the same ADMM strategy. Therefore, we are not sure about the convergence. Empirically, for the convex non-convex regime, the convergence can be seen, while for the non-convex regime, the value or the convergence sort of depends on the Lagrangian parameter beta. In this example, I would like just to show you that the function over a sphere is defined as a sum of these two components v and w, and the influence of the mesh on the result is not so how you can say it. The influence of the mesh, since we have used 4 different meshes, S1 to S4, the separation result or the decomposition result depends on the triangularization in terms that decreasing the area or the height of the triangle changes the maximum value of the gradient, and in that case, the higher the maximum value of the gradient, or the maximum non-zero value for the piecewise constant component in particular, the larger the separation region. In fact, for decreasing h, which is the height of the triangle, the ratio between small and capital M, so the maximum smooth gradient and the minimum non-zero gradient for piecewise constant component increases. And while having the same triangularization, but just enlarging the radius of the sphere, this ratio is preserved. Therefore, the SNRs computed increase with decreasing height, but stays the same if the ratio is constant. Here you can see the results that for S1, 2, and 3, which are the three different triangularization, containing from 8,000 to 131,000 triangles. Additional example for noiseless scalar fields and the decomposition results that we obtained. And I suppose quickly I should just mention what can we do as a further step in the following work, which is still under review. We have assumed a higher order regularization for the smooth component, and we have added another component representing the noise in our case. which we have modeled via the G-norm that I have mentioned earlier. Therefore, the data fidelity term is has just one function to tie the three components together, and the G-norm should handle the highly oscillating zero mean component, which can be also not just the texture, but also noise. Even in this case, the convexity can be achieved for phi, and it led us to still to a two-block ADMM for X and T. As some examples, this is a this is both denoising and decomposition at one step, where for this image, which has been corrupted by standard deviation 25, we have denoised for SNR going up to 32, and the components are down here. Which is really interesting, or what is really interesting is that the G-norm can handle the component quite well, since the estimated standard deviation for this component N is really close to the original standard deviation that we have applied. Also, as an application for soft shadow removal, once again, also can be applied as denoising, even though we have applied just a small standard deviation Gaussian noise in this case, because the resolution of this photo was quite low. Therefore, the noise component is not that much visible, but yeah. And also at last as a texture example, so traditional Barbara, which for which we didn't corrupt it by noise, but we were interested in how the G-norm could handle texture per se, and therefore the texture-free resulting image is this one, the two components. And one thing that can be noticed, that our design of the G-norm that we have used takes also the hair texture, or captures the small textures of the eyes, not just the higher oscillating texture of the scarf. So in conclusion, this work represents an enlargement of the class of convex non-convex variational approaches. It can be applied to simultaneous denoising and decomposition of noisy scalar fields into piecewise constant and smooth components, or adding a noise component or a texture component. There were two splits in this talk. The first one is the regularization split, which is a weighted combination of a quadratic term and TV-like non-convex term, and in the computational split, the ADMM-like minimization. And with references, I thank you for your attention.
Thank you, Martin, for this very interesting talk. So we are now ready for questions. So do you have any comments, or are you curious about something?
Feel free to ask.
Maybe I can start with one question,
Yeah.
which is about your lambda parameter.
Mm-hmm.
And I mean, it plays the role of a regularization parameter, right?
Yes.
So,
Sure.
since you're basically using lambda to set the A parameter of function phi, is it correct?
Yes.
I was wondering if you, I mean, how do you set lambda? Is it set a priori, or do you use some sort of discrepancy principle so that it changes along the iterations?
Yeah, we have used also continuation in order to see the influence of lambda, since a priori we didn't know what lambda to choose, such that the noise would be eliminated while the two components could still be tied together. So yeah, we have applied a sort of continuation in this case. So we calculated the results for a couple of values of lambda, and then maybe refine the subintervals for lambda.
But within the ADMM
Yeah,
iterations, or?
yeah. Or yeah, it could be we didn't incorporated it inside the ADMM. However, for some testing examples, let me just yeah, for some testing examples, as here, these are the SNR surfaces for changing eta and changing lambda to see where can we observe a plateau or a maximum value for mean SNR of all the three components, V, U, and W. Because U, of course, incorporates the noise, while V and W, we knew the ground truth, so we checked it against their ground truth. And based on these results, we then at least had some idea how to select the lambda value. Of course, it can be implemented directly as a continuation in the ADMM.
Okay. Okay, so in the end, I mean, the A parameter is set once for all, and you don't change it along the iterations. That's
the A parameter is set automatically based on the other
on that
parameters.
criterion. Okay.
Yeah, of course,
okay.
if of course in this graph here, the value of A changed because eta, both eta and lambda were changing. So for each point of this surface, the value of A was different, such that it would satisfy the convexity condition.
Okay. Okay. Thank you. And then just an appreciation comment about this.
Yeah.
I mean, the stuff, just to understand if your image is decomposable. That was really interesting. The fact that basically you see this bimodal distribution that tells you that you can separate. That's very interesting.
Yeah, because of course the question that can be asked is what happens if you apply it to real life images, but in real life images you usually are not sure what you should expect as the components themselves. On the other hand, at least some ideas. Yeah, let's say in this example, the rectangles could represent a barcode or a QR code, which are nicely piecewise constant images. And if you have a spotlight on them or a shadow as in this example, then some idea if it is or some idea what you should expect as the structure piecewise constant and the smooth component is there. Otherwise, it is not. Like, for example, in this case, the component W here can, me personally, I can explain it to myself as the lightening of that image.
Well, it is smooth somewhere.
Yeah, well, it is smooth everywhere, but it's really like the lightning you can see like in this part here, or the
On the
shadow.
face. Yeah.
Yeah, or the shadow that is casted by the scarf. So
Yeah. Thank you, Martin. So do you have any other questions?
Maybe I have a curiosity.
yeah.
Okay, thank you, Martin, for your great talk. I'm just curious to know, have you ever used other kind of meshes? Because you used, you show us that you can obtain different results with yes, these. And
Yeah.
have you ever tried to use different kind of meshes?
Well, what we wanted to understand in this example was to see how the mesh quality influences the result. So of course, you can have a coarse mesh, or you can have a really fine mesh. But also all three meshes are still so-called regular meshes, or at least the shape of the triangles is quite regular. The last one, S4, is so-called irregular one, where the valence of each vertex is not close to 6. That's for first, and for second also the triangles can be degenerated. As an example, it should just tell you that okay, you can work with both types of meshes, and the results should be quite good. Interestingly, for the irregular mesh, the SNRs we have obtained are even better than the regular ones. This is due to the fact that since the triangles in the irregular mesh are degenerated, the height of the triangles is even smaller than the height of the regular triangles. Therefore, even though the separation region width or length is smaller, or indicates to be smaller, it's does not influence much the result. And regarding the meshes or the different SNR values, it's something that we have observed, that if you focus just on SNR, it really depends what are the values or the absolute values of the components. Maybe I can no, I cannot. Maybe here. Yeah, for another example of the absolute value of or the intensity of the components can be seen also here, where for V the SNR is up to 23, but the SNR for W is just about 16. which does not mean it's wrong or it's not well separated. It means that the absolute or the combination of them, let's say this was 0.8 and this was 0.2 in order to create the image when we combine the two components. So for different, going back to different meshes, one irregular mesh is, for example, the horse or the vase. Both of them are irregular in this case. So yeah, we have used just the benchmark meshes that are free to be downloaded, but yeah, the study itself on the influence we did just for this example.
Okay, thank you.
Can I also continue with this argument, asking you one question? Okay, maybe I didn't, maybe I understood this wrong. Let's start with this. So a curiosity I have is this one. Is the refinement of the mesh somehow relatable with the texture you are going to find? And in this sense, you know, recently a lot of work is devoted to the to finding regularization which have local properties, and Monica as well is working on that kind of things. And here you're used, let's say, a total variation regularization, which is not considered to be as the best thing in the world nowadays. And what I'm thinking about is there a way you can adapt your mesh in a sense to have it more refined or less refined according to the different areas of the manifold, and obtaining, so let's say, a local effect, improving the results?
Partially, what you are saying has been used, for example, in this case here.
Okay.
Because the vase itself is not so well refined,
yes.
But a part of the mesh was refined in order to be able to sample the texture, in this case the QR code, onto it, because otherwise maybe a good midway to go would be to use different sampling of the function over the mesh itself, because since we have sampled it over as a piecewise linear signal over the mesh vertices, it for coarse meshes we obtained something like this. So the sampling is there. However, in the software, when you are trying to visualize it, the color gets diffused, even though the color itself or the values of the functions are two distinct values from one vertex to another. In the visualization, the software just creates a line in between them.
Yes.
To do this. For your other part of the question regarding the local properties, etc. Yeah, this approach is a sort of an alternative to what even Monica or and others are doing, because instead of using just one function that we are trying to recover, onto which we apply either a space variant parameters or a space variant regularizations, we divide the function itself as a combination of components with different properties. So I recall there is this skyscraper image as a benchmark that is used. Yeah, instead of applying something localized for different parts of that image, you can take it as a combination of something that is piecewise constant, something that is smooth, and something that has texture in it. So yeah, regarding the mesh is something that usually doesn't change.
Okay.
It's the domain that you have, and you don't modify the domain, but of course we could work around the parameters, or maybe apply something on the mesh. But as I was saying before, once you look, for example, at the gradient magnitude, this can be problematic in a way for textures, because if you have small triangles, the gradient magnitude there can be higher than what you would expect in an image.
Yes, I see.
A way to approach that would be to scale it somehow, to use the geometry of the mesh to make it yeah, scalable or scale free in a way that your parameters would not need to consider the mesh itself.
Okay. Good. Thanks, Martin.
Do you have any other comment? So if not, I think that we can thank Martin again.
Okay. Thank you.
With this Zoom reaction. Okay. And we'll see in 2 weeks for the next PRIMO talk. And have a good evening.